Now, let's look at example 3 on page 6 of slides 5-2. Okay, so with this example, I'm demonstrating to you why I'm recommending you to check the second order condition first. Okay, because it avoids efforts in vain. All right, so this function is minus 2x squared plus 14x minus 76xy plus 24y minus 2y squared plus 4. All right. So here, let's do the first step, which is check second order conditions. In order to check that, we need to start with first order. F partial on x, f partial on y. So f partial on x, the first term is minus 2 multiplied by the derivative of x squared, which is 2x, plus 14 minus, now you can write it alternatively above, right? Here, minus 76 by y, the entire thing is a constant multiplied to x. The derivative is, with respect to x, is then minus 76y, the slope term, right? For a linear case. So x to the power of 1, that's a linear case. Then for the 3 terms to follow, which are merely terms in relation to y or constant, it has nothing to do with x. So the derivative, the partial derivative with respect to x of the last 3 terms is 0. So we just omit them. So here, the first order derivative is minus 4x minus 76y plus 14. You see why we always put the constant in the end, because possibly, which is the case, as we are deriving the second order derivative, the last term is just disregarded as a constant. So f partial on y, the first 2 terms are merely terms in relation to x, so we can disregard. And then minus 76x, the entire thing is a constant multiplied to y, as here in this case, y is the only variable in your eye. So the derivative of that term is minus 76x, then plus 24, right? And minus 2 by 2y, in which 2y is the derivative of y squared. And the last term is constant. Again, in derivative, we just disregard. So here, it is minus 76x minus 4y, okay, plus 24. That is the second derivative. The second possibility of first order derivative. Okay, so let's check the second order. fxx, fyy, fxy. So fxx is to take another derivative with respect to x of f partial on x, which is the first one. So fxx is minus 4. The second term, disregard. Third term, disregard as constant when we only view x as the variable. fyy, here we have another minus 4. Right? The first minus 76x, disregard, because that has nothing to do with y. 24, disregard, that's a constant. fxy, then you're taking derivative of f partial on x with respect to y. So the first term and the third term have nothing to do with y, right? They are disregarded, and the derivative of minus 76y is minus 76. So now let's turn to the previous reference, which is this. Okay, So fxx, fyy, those straight or direct derivatives, in this case, are both smaller than 0. We are on the track of determining, okay, this stationary point that the first order conditions of this question defines could possibly be a maximum, but we need to check the second row, which is the cross condition. All right, the cross condition is fxx fyy is greater than fxy squared. Let's check it. Fxx fyy is -4 by -4, which is 16, and fxy squared is -76 squared, which is greater than 16. So this condition is violated. So here we don't have a maximum nor a minimum. Then there is no need for you to go to second step, which is to solve for the first order conditions. If instead you start with solving the first order conditions, you need to solve, okay, -4x minus 76y plus 14 equal to 0, and solve the second one equal to 0. Those are the first order conditions, right? And it could be a hassle for you to solve. It's not easy to solve those system equations by hand, I would say, at least. So here, since we don't have a maximum or a minimum, we can skip the second order, the second step, which is the first order conditions. And we can report no maximum nor min for this function in question. Okay, that demonstrates to you why I require you to check the second order first and then do the first order. But why you're doing the second order? Because you still have to figure out the first order derivative for the basis of deriving second orders, right? Here, you get partial credits for deriving the correct first order derivatives. And then later on, if you do have a maximum or minimum, you can directly take the first order, copy them, and set them equal to 0 and solve the system equations, which makes your solution more formulaic, easier to trace.